Uniform circular motion. Okay, so by definition, right, uniform circular motion, for you to have uniform circular motion, you need your particle or your ball or whatever, or the car, whatever it is that's going around, you needed to do two things. You needed to go around a circle, a perfect circle, right? And it needs to go around that circle at constant speed, or the magnitude of velocity has to be constant. These are the two conditions for you to have uniform circular motion. So what do we mean by that? If I attempted to draw a circle here, right? Assume this is a perfect circle. Actually, I can draw that a bit better. Okay, so say something that looks like this, right? And this is the center of the circle, right? And you have a ball right here, and it's connected via a string. At this point right here, the velocity of the ball will point directly upwards. It will be tangent to the circle, so this is V, right? And then at the point at the top, so say right here, right? The velocity of the ball will have the same exact value, or sorry, the same exact magnitude, so same speed, so it's still V, but it has a different direction. So I have a change in velocity, right? Because velocity depends on both direction and speed, right? So how fast is it going, the magnitude of velocity, and where is it going? Is it going left, right, up, down, right? So here the speed does not change, but the direction does. And by definition, if I have a change in an object's velocity over a given period of time, then I have acceleration. So in this case, one might ask, okay, where is that acceleration? Well, the acceleration of an object in uniform circular motion is always pointed towards the center. So if we were going to take this scenario here, the acceleration would be pointed this way, towards the center. And we call this acceleration acentripetal, or for AC for short, right? And then at this point up here at the top, then acceleration is pointed directly towards the center again, acentripetal. Right, no matter where you took it. If you took this point right here and you wanted to know where is acceleration, its acceleration is always towards the center. So this is a centripetal. And then again, you might say, since I have an acceleration, I need to have a force. And yes, you do have a force, and this force has the same direction as the acceleration, because the direction of a force depends on the direction of acceleration, right? So the force would be pointed towards the center as well, and similarly we call this force F centripetal. So F centripetal. And if you wanted to relate F centripetal with A centripetal, then that's just Newton's second law. So you say F centripetal is equal to M times A centripetal. Okay, so we said that F centripetal is equal to the mass times A centripetal, which are just the force that points towards. What is F centripetal? F centripetal is the net force, right? So let's define that. FC is the net force that points towards the center, towards the center. F centripetal is not a real force. It's not like force of gravity. It's not tension of a spring. It's not tension of a rope. It's not electrostatic force. F centripetal is just the name that we give to the force that points, or the net force that pulls you towards the center. So if we think about a car going around the roundabout, right? That force would be friction. If you think about, say you have a ball and you're swinging this ball in a circle, then F centripetal would be the tension force if it was a horizontal circle. And sometimes F centripetal is a combination of forces. F centripetal is just the net force that points towards the center, right? Now let's write some more formulas. You've got F centripetal equals mass times acceleration centripetal. Well, what's acceleration centripetal? Acceleration centripetal is equal to velocity squared over r, right? Where r is the radius of your circle. And another way that you can find velocity is you can say velocity equals from distance over time, right? What's the distance that something covers in a circle? It'll be the circumference of the circle, right? But the circumference of a circle is 2 pi r. And then what's the time? The time is just going to be the period, right, for it to make one revolution. So the amount of time it takes for a ball that say this is your circle, the time would be, if you started at this point, it would be the amount of time it takes you to come back to this exact point again. That's what time is. And then finally, you've got one last formula, which is that frequency is equal to 1 over t, where t is the period. Now, what does frequency give you? Frequency is just the revolutions per second, right? The RPM. When you hear of RPM, you're thinking about frequency, right? These are the most important formulas that you're going to need to solve any uniform circular motion questions. Okay, so let's take an example. In this exercise, it states that you have a 2,000 kilogram car moving along a circular curve of radius 200 meters with a speed of 25 meters per second. And it asks, what is the minimum coefficient of static friction between the tires and the surface of the road to guarantee a safe turning without any skidding? So let's draw this out, right? If we take a top view, right? So top view. And so this would be our car. You're free to draw it anywhere you want, but say this is your car, right? The radius, they gave you the radius. They said radius, so if this is the center, then this right here, r, is equal to 200. So 200 equal r, right? And now they want to ask you, and they told you that it's moving as well. They gave you velocity. So right here, v is equal 25 meter per second. And they want to know what is the minimum coefficient of static force between the tires and the surface of the road to guarantee safe turning. So for me to have safe turning, i.e. for me to continue having this move in uniform circular motion, I needed to guarantee one condition, right? And that condition is that F centripetal is equal to the mass times A centripetal. Right? This is the condition that I need to guarantee. Now, what is F centripetal in this case? Well, we look at the car and we think, okay, what is the force pulling the car towards the center? Right now, the car is trying to skid this way. It has inertia to go this way, right? When it's turning, not specifically in this instance, but when it's turning, right? It'll be, for example, if the car was over here, it would be attempting to kind of skid this way. And so the only thing keeping it, the thing that's pushing it towards the center, the force, would be the frictional force. So in this case, static friction is actually equal to F centripetal. So you can say FRS is equal to the mass times AC. Now, what is FRS? We know that static friction is equal to the normal force, or in this case, it wants the minimum coefficient of static friction. So we're just going to say the normal force, which is going to be 2,000, which is the mass, times gravity. We can say gravity is 10 for the sake of ease of calculations. And then multiplied by the coefficient of static friction, we'll call it mu s, must be equals to mass, which is also 2,000, multiplied by AC, and we know that AC is equal to, okay, so AC is equal to V squared over R, right? So now just substitute, instead of AC, substitute V squared over R. We know V is 25, so that's just 25 squared over R, which we know is 200. Then you solve for mu s. So you cancel 2000 with 2000, you divide by 10, so you get 25 squared over 2000, or 625 over 2000. So you get that mu s, the minimum mu s, so the minimum mu s is equal to, so mu s is equal to about 0.3125. Okay, so let's take another example. In this example, it says that a 2-kilogram bucket is circulated in a vertical plane of radius 1.5 meters. The fact that it's a vertical plane matters, and I'll show you why. The magnitude of tension in the rope at the lowest point is 30 newtons, and then it asks you find the speed of the bucket at its lowest point. So let's draw what we know, right? If this is the center, then the distance from the center to the lowest point, this distance right here, is equal to 1.5 meters. Right, and then here is your bucket, right here. So let's draw the free body diagram of this bucket, right? If this is the bucket, then you've got a force upwards, which is tension. Tension is equal to 30 newtons. And you've got a force downwards, and this is its weight, or its the gravitational force, right? So Fg, which is equal to its mass, which is 2 kilograms times the gravity, which we'll say is 10, again, to make calculations a bit easier. So Fg is equal to 20 newtons. And now all you have to do is just say F centripetal is equal to mass times A centripetal, where in this case, F centripetal is actually, this is why we said F centripetal is the net force pointing towards the center. F centripetal is the tension, right? So F centripetal is tension minus Fg, so it's 20 minus 30, so it's 10, right? And then this becomes M times A centripetal. A centripetal, as we know, is V squared, which is what we're trying to find, over R. So then this becomes 2 into V squared over 1.5, and then this just becomes 2V squared over 1.5, right? So just 2V squared over 1.5, and then you take 1.5 to the other side. Actually, divide by 2. No, multiply by 1.5. It doesn't matter. Multiply by 1.5 first, divide by 2. You'll get V squared equals 7.5. So V squared equals 7.5. So then V is equal to radical, or square root, of 7.5. And that's your answer.
That'll be it for lesson 6.2, circular motion. If you have any questions or want to ask anything at all, you can ask it down below in the comment section or in the server, and good luck in the finals.